All right, so we're getting into the last unit here. I hope everybody's excited. Um, the last subunit that we're going to do is the universal law of gravitation, and we're going to have some physics involved in this, and I'm going to have a couple examples for each thing. But other than that, it's going to be pretty much on you to look over the PowerPoints and make sure you understand what's going on. And if you don't understand, make sure you contact me so that I can help you so that we can rearrange some sort of tutoring or something to make sure that you know what's going on with these laws of gravitation. The main thing that I want you to know these for is for the quiz at the end and then the unit post-test at the end of this unit. The final exam doesn't have all that much stuff on physics on it, so you won't have to worry too much about that. So our objectives are going to be to explore how the universal law of gravitation affects all objects, explain the relationships among gravitational force, mass, and distance, and solve some problems that involve the universal law of gravitation. So we will be doing physics. Woohoo! Everybody be happy about that. I know you're not happy. So describe the effect of gravity on an object, especially on Earth, because that's kind of what's important to know, because we are on Earth. So forces. A force is just any action that has the ability to change an object's state of motion. So there's going to be push or pull forces, tension, friction, and gravity. There are other forces, but these are the ones that are mainly the ones that we talk about in physics. So contact forces are going to be like push and pull forces, tension, and friction. And non-contact is going to be something like gravity. It's a constant. So here's a guy pushing a cart. That's push force. If he pulled it, it'd be a pull force. Here we're implementing pull forces and tension. So that right there is tension. When you're pulling a line taut, that's what tension is. It's a lot of tension. This one's going to be friction. So as this guy is pushing, this guy putting his heels into the ground is going to create friction. It's going to make it harder for this guy to push. And then here's our non-contact one. It's gravity. So it's just an apple is ready to fall. It gets pulled and pulled and pulled towards the center of the earth, and then eventually it falls due to the force of gravity. Nothing's actually touching that. So what is the universal law of gravitation? Well, it's Isaac Newton's baby. He figured out the natural law that states that the force of attraction between two objects is affected by the masses of the objects and the distance between the objects. So this is his classic, an apple fell out of a tree and hit him on the head. He went, oh, hey, there's something going on to where, that apple wasn't being pushed. There's some sort of invisible force that I don't know about yet, so I need to figure that out. And then he realized that it affects pretty much everything in the planetary system. So, what is a gravitational field? We're going to be talking about gravity here. A gravitational field is just a field that exists around an object due to its mass. So when you have a lot of mass, you have more of a gravitational field. So you're going to be able to pull things into you that have less mass. So the strength of the field is directly proportional to the mass of an object. So that means that if one increases, the other will too. So directly proportional means like you raise the mass, the force of gravity will also raise. So here's some examples. 2m, that's 2 mass, equals 2f, 2 of force of gravity. If you change that to 1, it would also be equal to 1. So, F is force due to gravity and m is mass. So that's that direct relationship. So inversely related, the gravitational field is inversely related to the square of the distance between the center of two objects. So as you get further away, increasing your distance, the gravitational force will decrease. So this is just the opposite of directly proportional. So when things are directly proportional, they increase or decrease and decrease together. If they're inversely proportional, one increases, one decreases, or on the other hand, one decreases, the other increases. So that's what you have to realize with inversely proportional and directly proportional. So with distance, since it's the square distance right here, that's the square of the distance is the force. So if we get 2d, then we're going to do 1/2 because 1/2 is the inverse of d. So really what you do is you just put a line over it, like divide it, and then put a 1 on top. Sorry, you put a division line above it and then put a 1 on top, because that's the inverse of 2 is 1/2. and then you have to square that 1/2 to get the force. So squaring 1/2 gets you 1/4. So that's if distance is 2, you get 1/4. So if distance is 1, you're going to get 1, because if it's 1 and you square 1, that's 1. But then if the distance is 1/2, this is where it gets interesting. The force, the inverse of 1/2 is 2, just like how the inverse of 2 is 1/2. So the inverse of 1/2 distance is 2, and then you have to square that, so you get 4. So you see how right here it's 1/4 if you get 2, if you have 1/2, it's 4. So that's just the inverse proportionality. As distance gets smaller, force goes up. As distance gets larger, force goes down. Whereas if mass goes up, force goes up. And so then here is just like a wonderful PowerPoint slide on how to remember this. Go ahead and take a picture, whatever, pause it, whatever you need to do. So this is distance and then also mass. It looks like, oh, down here you get 2m, 2m, 2d, you're just going to get 1f. If you get 1m, 1m, 1d, it's going to be 1f. If you get 2d, like we said, 2 distance, the inverse of that is 1/2, then you square that and you get 1/4 is the force between these two masses. And then if you get 1/2 that distance, the inverse of 1/2 is 2, you square that, you get 4. So that's the force of these two masses together. And then so going to masses, if you add 2m or 2m with 2m, that's 4m. It's going to be the exact same thing as 4f. So they're equally proportional. So you're multiplying these. So 2 times 1 is 2, 1 times 1 is 1, 2 times 2 is 4, 3 times 1 is 3. So that's the directional proportionality between those. So just, take a look at this. If it really confuses you, then go ahead and let me know, and I can help you with anything. So we also have a formula to calculate gravitation. Hold on a second. Let's see how much time we have. Okay, so we'll do this first example and then possibly do another video. But so this is the formula to calculate gravitation, and this is what Isaac Newton came up with. So F of g, which is the gravitational force, which is measured in newtons. Then we have g, which is the gravitational constant, which we've already figured out, which is 6.67 e to the negative 11. So e takes place of times 10 to the, and this is just like when we have many different exponents or zeros, then we put times 10 to the. So this is really times 10 to the negative 11 means we take this decimal place and then we go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then for all of those blank spots, we put a 0 in. So it's 0.00000000067. So it's a really small number. And then that's going to be calculated in Newton meters squared over kilograms squared. So M1 is going to be the mass of object 1. M2 is the mass of object 2. That's not 1, it's 2. And then D equals the distance between object 1 and 2. So we already know this. We already looked at this in the previous section right here. Here's M1, here's M2. What are their masses? Here's its distance. We know the proportionality between these. What we don't know is the force of gravity. So we know the gravitational constant. We'll know mass of 1, mass of 2, and the distance. And so then we'll be able to plug those numbers in and figure out F of g. So here's an example. The mass of Earth is 5.98 e to the 24th kilograms. So remember that e just takes the place of times 10 to the. And so then the mass of the moon is 7.35 e to the 22nd kilograms. So if you see Earth is to the 24th, moon is to the 22nd, that's a lot of exponents. That's 2 more zeros. So Earth is much larger than the moon. And then the distance between them is 3.84 e to the 8th meters. Okay, so what is the gravitational force? That's what we're going to figure out. So what we always do with equations is we figure out what we know, we figure out what we don't know, and then we input those numbers into the equation and we'll get a number at the end. It's a lot more simple than it seems because it's a lot of crazy big numbers, but really you're just putting them in here, putting them in a calculator, and then being done with it. So what we know, mass of 1, that's going to be Earth. Right here we got that, 5.98 e to the 24th kilograms. Mass of the moon, which is m2, that's 7.35 e to the 22nd kilograms. We know the distance between them, d, which is 3.84 e to the 8th meters. And we know the gravitational constant right here, g, that's 6.67 e to the negative 11th Newton meters squared over kilograms squared. So what we're trying to figure out is f of g, the force of the gravitational force right there between the two objects. So the solution is we just plug those numbers in. G right here, we put in 6.67 e to the negative 11th Newton meters squared. Remember to get your units in there. I just took the units out of here because it looks really crazy when you put it in a solution. So remember those Newton meters squared right there over kilograms squared. So then you multiply that by m1 times m2, so the mass of the moon by the mass of the earth, and then you divide all of that by the distance, and that's 3.84 e to the 8th, and that's really what this is 384,402 squared. So, because you get that squared right there, remember that distance squared from our previous slides here. Distance squared, distance squared, distance squared, all that stuff. We talked about that. So then f of g is going to equal 1.98 e to the 20th newtons. And so basically what you did was you put all of those units in there, all that in the formula, and then you just cross out all of the newtons that you, or the units that you see. So that's what they did here. They had these units. This is g. This is going to be in meters. This is going to be in meters. And then this is going to be in just meters as well. Yeah, so, oh yeah, this is Newton meters squared over kilograms squared. Okay, so what they did was they took the meters out, and then they got rid of kilograms right here, and so all that was left was newtons for the f of g. So you just really go through the units. You put all the numbers in there together, and then you go through the units at the end, cross the units out, and whatever you're left with is going to be usually n if you're looking for f of g. So here's just another example. Pause it, take a look at this, try and do this yourself, write it down, figure out the units, plug the units in here, and then at the end cross the units out that you see on the bottom and on the top. So whichever one has like a divide symbol in, you can cross those out next to a multiply symbol. So kilograms is going to be there, meters is going to be down here, so then you'll just be left with newtons. So again, if this is confusing, let me know. We have to tutor this to you if it's confusing to you because it's hard to do over a video. Okay, and so you can rearrange the universal law of gravitation formula to find all sorts of other variables. So if you want to find the mass of 1, m1, then all you do is you're going to just divide out f, really, and multiply r. And so you're just going to kind of flip this equation right here. You're going to flip this bad boy over and multiply f in. So you're going to just get f of d. This is really d. It says r, but we use d for edgenuity. So we're going to do f d squared over the force of gravity, which is a constant, times the mass of the second object. So, if you have an unknown m, but you know m2, m1, if you have an unknown m1, but you know m2, then you can find out all of that information if you have the force due to gravity, the gravitational constant, and the distance. Whereas, you can find the distance by square rooting that whole equation, because right here you've got r squared, so to get it out you need to square root it. You'll flip that out, you'll switch f to the bottom here, because you'll have to divide f out, and so then you'll get r equals the square root of that first equation, and then you can figure that out as well. Okay, so we're going to do another example, but before we do that, I'm just going to pause the video and then we'll have another one on this.